Hello everyone, my name is Shadib Hussain and the project that I'm working on is can we use a spectrogram that is generated from a heart auscultation to identify any kind of abnormal heart conditions. We would particularly focus on a condition called PDA, which is patent ductus arteriosus. You could see the diagram on the top of my screen where what is a PDA explained very clearly through an illustration. A patient with a PDA condition would have a blood flow going from the aorta to the left pulmonary artery. Under normal condition, it doesn't exist. But a patient with a PDA would have an abnormal blood flow occurring between aorta and left pulmonary artery. Now, my project would try to use the spectrograms generated from a normal patient and a patient with a PDA and see whether the spectrogram can actually can be used to identify that heart condition. You would see on the right hand side is the spectrogram generated for a normal patient from the auscultation. Similarly, on the right, you would see is the spectrogram that is generated with a patient with a PDA condition. Now, if I click on this one, so here's a MATLAB code you could see over here. I'll explain to you what's going on, but when you run it, this is with a normal patient. This is for a normal patient. You could see over here, that's the MP3 file that's been used. You will see this is the spectrogram that's generated over here. Similarly, if you change it to a PDA, you would get this corresponding spectrogram. But let me explain to you how this can be generated and the whole process in my project. So two conditions has been analyzed. One is a patient with a normal heart. As you could see over here, the reference of the diagnosis is given over here, where there is no opening. Case 1 is a normal heart. In case 2 is a patient with a PDA, where there is an opening between the aorta and the pulmonary artery. Now, if you're trying, so what we try to do is from a database, we try to get auscultation waveforms. Now, if I do have a Python code for this one. Just minimize it just to make sure that, yes. So let me just run this one. So this code is with for a PDA waveform. So let me just run it. You could see over here, it is generating a real-time spectrum. Okay, this is the input signal and this is the frequency spectrum. You would be able to see it, and the same thing can be applied for a normal heart. However, the main problem is unless you are specialized in that field, it would be hard to quantify it. So that's why, as an engineer, my project would be to design kind of a program that can be used by physicians to see whether we can use this auscultation waveforms to identify an abnormal heart condition. So the first step I try to do is to generate a MATLAB code that would help me get the Fourier transform. So you would see over here, this is the code that would help you get the Fourier transform, which is converting this waveform from time domain to frequency domain. If I run this code, you would see one is for the normal patient and one is for the PDA patient. And this is the time domain signals. Now let me explain to you what happened. So over here, the first step I try to do is to visually analyze the signal. So this is in the time series for the normal as well as for the PDA patient over here. So you would find that you can easily use MATLAB to convert this time domain signal into a frequency domain signal. Sometimes it might not be very accurate because the signals, the frequency domains would be very clustered. And the first step, that's why I would suggest, is to perform short-term Fourier transform. Now, a short-term Fourier transform, in this case, we are trying to truncate the signal to only 40.46 seconds. The reason is because the heartbeat could range anywhere between 0.46 seconds to 1.2 seconds. So for this project particularly, we try to truncate the signal to 0.46 seconds and try to see any dominant frequencies that are present over there. Now, let me just enlarge it. You would see over here, this is for a PDA patient. Now, I tried to normalize the frequencies, so you would find that there's a high peak at 132 hertz, followed by a second peak at 173 hertz. These two are dominant peaks, quite visible in a PDA patient when we did Fourier transform, a short-term Fourier transform, reducing the time domain to only 0.46 seconds. Similarly, when we try to do it for a normal patient, we try to see that there are quite a couple of different frequencies signal present in those. One is at 60 hertz. The other one, the highest peak was at 119 hertz, which is quite different from 132 hertz visualized in a PDA patient and 180 hertz. So you would find that there are different frequencies. There's a frequency shift occurring whenever a patient has an abnormal heart condition. So this actually let me investigate the process further and try to see what's happening. Now, you can use a spectrogram. So this is the MATLAB code that I used to generate the spectrogram. So this is the spectrogram graph. Now over here, I'm trying to just analyze the normal one. So I'm just running it. It was just same as the beginning of the slide as I showed you. And this is the spectrogram generated for a normal heart. And you would be able to see the signal. This is the time domain. This is the frequency domain, and this is the intensity. Now, so this is the parameters. The Kaiser window for the block length, so R is 256, beta was kept at 5, and FFT length was also kept at 256. For a normal heart patient, the highest energy density was observed between 350 to 400 hertz range, whereas for a PDA patient, the energy density was considered more on the 0 to 60 hertz range, and for anything greater than 350 hertz range. Now, the problem is sometimes the short-term Fourier transform might not be an accurate representation. Why? As it was mentioned in certain literatures, the major challenge of the short-term Fourier transform is they cannot represent the acoustic associated with the nonlinear behavior of the human hearing. Now, in order to replicate that, we have to pass it through a filter. Now, what kind of filter are we using? So we are using a gamma tone filter. So a gamma tone filter, this how to generate a gamma-ton filter in MATLAB is given very clearly in MATLAB. You would be finding the description in their documentation. This is the equation associated with a gamma-ton filter as long as its time period is greater than 0. All the specifications are given over here, but once that, so what we try to do is we pass the normal signal and the one with the PDA patient through, now pass it through a gamma-ton filter. Okay, so we try to pass the signals through a gamma-ton filter, and we try to see the spectrogram as a function of time as well as function of frequency. Now, what we try to analyze the time, frequency, the amplitude, and the energy distribution. Now, if you're trying to analyze it for a longer period of time, it becomes very difficult to identify the most significant features. So we try to truncate it again to 46 seconds in order to get a more visual representation of how the energy distribution and how the frequencies, amplitude, are changing as a function of time. So this is the MATLAB code. This is dominant MATLAB code, I would say, because this can be used by any physicians to actually see, once you pass through the signal, pass through a Fourier transform, pass it through a gamma-ton filter, this is what's being generated over here. So let me just run it. So when I'm running it over here, it takes a couple of minutes. It because it passes through a gamma-ton filter, it would take a couple of seconds. And you could hear a sound as well. I'm not sure whether let me run it again, just one more time. Okay, so this is the spectrogram still running. That was the spectrogram before passing through a gamma-ton filter. And this is after passing through a gamma-ton filter, we get this one. So this is after passing through a gamma-ton filter. Okay, you would see over here, the time is kept between 0.46 seconds, and this is the intensity, and this is the time frequencies. So I also try to truncate the frequencies because I'm trying to observe it for a small frequency domain. I do not want to analyze over a longer frequency range because then the resolution becomes very hard to analyze. So I try to over here it's given the time axis is kept at 0.46 seconds, and the frequency limit is set to 500 hertz in order to visualize how the change in the spectrogram is occurring. Now, for a normal person as well, for a technician, it will be much easier, but for a normal person as well, you can see a clear distinction between the spectrogram for a normal patient as well for a PDA patient. As you would see over here in a normal patient, the frequency over here, the energy distribution is more or less, I would say it's kind of uniform, whereas in this case for a PDA patient, it's kind of concentrated over here, and it is frequency dependent as well. And this is for a normal patient as a function of frequency, as a function of time. So this one is a function of time, and this is as a function of frequencies. When the frequency is here, so the frequency is here, this is the time axis, and here this is the time axis, and this is the frequency. So to conclude what we did over here, the spectrogram analysis would help us understand the energy distribution or the amplitude and also the frequency as a function of time that can be used for any preliminary diagnosis in case those are not clearly identified by a specialist. So we performed a short-term Fourier transform with that of a patient with a normal heart and that with a PDA patient. And we tried to identify if there is any dominant peaks. We realized that for a normal patient, the peaks was at 60 hertz, 119 hertz, and 180 hertz. As well, in contrast, a PDA patient had frequency peaks at 132 hertz and 173 hertz. However, the problem with short-term Fourier transform, it does not take into account the nonlinear behavior of the auditory system. So that is the reason why we pass it through a gammaton filter. And once we pass it through a gammaton filter, we try to get the spectrogram. Now, for the spectrogram, we try to truncate the signal to only 0.46 seconds because that's the normal heartbeat. And also we try to set this frequency limit to 500 hertz because we are not expecting very high frequency peaks in when it comes to the heart signal. So we try to truncate the signal to only 500 hertz, and it will also save us computational cost. And we try to see is there any difference in the spectrogram generated from a normal patient as well as that from a PDA patient. And we saw in the previous spectrograms that there is clearly a distinction observed. However, we need to do more studies in order to see that this is actually repetitive. And the reason why I assume is that there's a difference in the spectrogram is because there's an extra opening between the aorta and the pulmonary artery, right? So because there would be an extra opening, there would be an extra flow of blood occurring. So there would be a change in pressure occurring as a function of time because now that could be the reason why there would be a difference in the spectrogram generated for a normal patient as well as that from a PDA patient. So the quantitative analysis could help or complement a physicians who are specialized in that field and can be used in addition as a preliminary diagnosis not just for PDA patients, but also for other people with abnormal heart conditions. And the same process can be applied for different kinds of heart conditions in order to see whether the process is replicable as well. We can do machine learning and artificial intelligence to this process to make the system more automated. However, I suggest that this could be a good step to first get the ball rolling and help the specialist in identify abnormal heart conditions. Thank you again. And this, as you could see clearly, again, I'm just ending it with this note that there is clearly a distinction in the spectrogram for a patient with a normal heart as well as from with that one with a PDA. Thank you again. Have a great rest of the day.